Synchronous machines are everywhere, powering our world in ways we often take for granted. They're like the unsung heroes of electricity, tirelessly working behind the scenes. These machines always run at a constant speed, perfectly synced with the power grid's frequency, ensuring stability and efficiency. There are two main types of synchronous machines: generators and motors, each playing a crucial role. Generators create electricity by converting mechanical energy into electrical power, fueling our homes and industries. Motors do the opposite, transforming electrical energy back into mechanical force to drive all sorts of machinery and devices. Think of a giant water wheel connected to a magnet, a simple yet powerful analogy. As the wheel turns, it spins the magnet, creating a rotating magnetic field that is essential for electricity generation. This rotating magnetic field interacts with coils of wire, inducing an electrical current that powers our world. That's a generator in a nutshell. Motors, on the other hand, work in reverse. They use electricity to create a magnetic field that interacts with other magnets or coils, generating rotational force to power everything from fans to electric cars, making our lives more convenient and efficient. Now, let's dive into the heart of our topic. Armature reaction, a fascinating phenomenon in electrical engineering. Imagine a synchronous machine humming along, generating or consuming power, working tirelessly to keep everything running smoothly. Inside, there's a constant interplay of magnetic fields, an invisible dance of forces. The rotor, the spinning part, creates the main magnetic field, which is crucial for the machine's operation. But the armature, the stationary part with its coils of wire, also generates its own magnetic field when current flows through it, adding complexity to the system. This is where things get interesting, as these fields don't just coexist, they interact. Armature reaction is the interaction between these two magnetic fields, a crucial aspect of machine dynamics. It's like a magnetic tug of war, influencing the overall magnetic field within the machine, constantly shifting the balance. This interaction can either strengthen or weaken the main field, depending on the power factor, which is a measure of efficiency. Think of it like two magnets near each other, their forces interacting in a delicate balance. Depending on how you align them, they can either attract or repel each other, demonstrating the principles of magnetic interaction. Armature reaction is similar, impacting the machine's performance in significant ways, making it a key factor in electrical engineering. The power factor tells us how efficiently electricity is being used. A lagging power factor occurs when the current lags behind the voltage, often seen in inductive loads like motors and transformers. In this scenario, the armature reaction actually strengthens the main magnetic field. It's like giving the rotor's magnetic field a little boost. This might seem like a good thing, but it can lead to increased iron losses and heating within the machine. Imagine you're pushing a swing. If you push at the right time, you'll make it swing higher with less effort. But if you push at the wrong time, you'll work harder without much result. Lagging power factor is like pushing at the wrong time, making the machine less efficient. Now, let's flip the script. A leading power factor occurs when the current leads the voltage, commonly seen in capacitive loads like capacitor banks and lightly loaded transmission lines. In this case, armature reaction has the opposite effect. It weakens the main magnetic field, reducing the machine's overall efficiency. It's like trying to run with a headwind, making it harder to achieve the same output. Think about trying to push a heavy object uphill. It takes more force and effort to move it compared to pushing it on a flat surface. Leading power factor is like pushing uphill, making the machine work harder. Section 5. Unity power factor, a balancing act. The sweet spot for a synchronous machine is unity power factor. This means the current and voltage are perfectly aligned, resulting in the most efficient operation. At unity power factor, armature reaction doesn't directly strengthen or weaken the main field. It's like a perfect balance, where the magnetic fields coexist without significantly affecting each other. Imagine a seesaw perfectly balanced with two people of equal weight. Neither side goes up or down because the forces are equal. Unity power factor is similar, creating a stable and efficient operating point for the machine. Section 6. Practical implications, from generators to motors. Understanding armature reaction is crucial for both generators and motors. In generators, it affects voltage regulation, the ability to maintain a stable output voltage under varying loads. For motors, armature reaction influences torque production, the twisting force that makes things spin. Too much or too little armature reaction can impact the motor's efficiency and performance. Imagine a bicycle generator powering a light. As you pedal faster, the light should get brighter. But if the generator can't handle the increased load, the light might flicker or dim. That's poor voltage regulation, partly influenced by armature reaction. Similarly, a motor needs enough torque to start and run smoothly. If armature reaction weakens the magnetic field too much, the motor might struggle to start or operate efficiently. Section 7. Mitigating armature reaction, keeping things in check. This section delves into the critical methods engineers use to manage and mitigate the effects of armature reaction in electrical machinery. Engineers have developed various techniques to mitigate the negative effects of armature reaction, which can otherwise lead to inefficiencies and performance issues in electrical machines. These methods help maintain efficiency and improve performance, especially under varying load conditions, ensuring that the machines operate smoothly and reliably. One common approach is using compensating windings, additional coils placed within the machine to counteract the armature's magnetic field. This technique is essential for balancing the magnetic forces within the machine. It's like adding another person to the seesaw to maintain balance, even if someone changes position. This analogy helps visualize how compensating windings work to keep the system stable. Another technique involves adjusting the field excitation, the current supplied to the rotor's windings, to compensate for the changes caused by armature reaction. This adjustment is crucial for maintaining the desired performance levels. This helps maintain a stable magnetic field and consistent performance, which is vital for the longevity and reliability of the machinery. Think of it like adjusting the tension on a rubber band. The right amount of tension is necessary for the rubber band to function properly. Too loose, and it won't provide enough force to be effective. Too tight, and it might snap, causing potential damage or failure. Adjusting field excitation is like finding the right tension for optimal performance. It ensures that the machine operates efficiently and effectively, without any risk of overloading or underperforming. Section 8. Wrapping it up. Key takeaways. So, there you have it, armature reaction in a nutshell. It's the magnetic interaction between the rotor and armature fields in synchronous machines, influencing their performance. Remember these key takeaways. Armature reaction can strengthen or weaken the main magnetic field, depending on the power factor. Lagging power factor boosts the field, while leading power factor weakens it. Unity power factor is ideal, creating a balanced operating point. Armature reaction affects voltage regulation in generators and torque production in motors. Various techniques, like compensating windings and field excitation control, help mitigate its negative effects. Understanding armature reaction helps us design, operate, and maintain synchronous machines for optimal performance. These machines play a vital role in our electrified world, quietly and reliably powering our lives.